In this video, we're going to talk about section 10.4, which is polar coordinates and polar graphs. Our objectives are to understand the polar coordinate system, to rewrite rectangular coordinates and equations in polar form and vice versa, to sketch the graph of an equation given in polar form. I might use my calculator to do that in a second. And to find the slope of a tangent line to a polar graph, and then to identify several types of special polar graphs. I'll just refer you to your textbook for that. So let's go ahead and get started here by defining the polar coordinate system. So we're going to fix a point O called the pole, which is like the origin in our system. And we're going to construct from the pole an initial ray called the polar axis that's going to go out in what looks like the positive x-axis direction. And then we are going to rotate an angle theta that's positive angle measurement is going to be measured counterclockwise. Negative angle measurements are going to be measured clockwise, just like they were in trigonometry when we measured angles. And so it looks kind of like this, where r is going to be this directed distance, kind of like how you thought of on your unit circle that all the points were one unit away from the origin, and that's what made it a unit circle there. And then you have theta, like we said, was measured counterclockwise from this polar axis. And you just never even thought that you were talking about polar coordinates there. But I already mentioned last time that we had these somewhat polar definitions where we said cosine theta was equal to x over r, and we called this x, and we called this r, and we called this side here y. And so we said this is actually getting into the conversions that we're going to do here. And so x is going to be r cosine theta, and sine theta is equal to y over r. So y is equal to r sine theta, and tangent of theta is equal to y over x. And we can use the Pythagorean theorem to say that x squared plus y squared is equal to r squared. There's going to be our four conversions that we're going to talk about in just a little bit, but I'll introduce them right now while I have this this x, y, r, theta triangle, this angle and standard position that we're talking about. So let's go ahead and let's look at some examples here of points that are in the polar coordinate system. So I can think about theta equals a constant as a line here. It's going to actually go in both directions. And r equals a constant is going to be a circle. And where the circle and the line intersect one another, I'm interested specifically in the ray that goes from the pole in this direction of that angle. I'm really not interested in the other side of the line unless r is negative. If r is positive, I'm moving from the pole out in this direction of this angle. So I can just look at that ray, and where that ray and that circle intersect one another, that's where my polar coordinate is, where r equals 2 intersects with theta equals pi over 3. There's 2 pi over 3. So now I can have negative angles also that are measured clockwise. And so this array right here can be thought of as theta equals negative pi over 6. I've rotated pi over 6 in the clockwise direction, and I'm somewhere along this line, and I want to go a distance of 3. 1, 2, 3, right there. 3 steps will get me to my point, but I don't have to turn clockwise. I could have turned more degrees or more radians and turned counterclockwise here and turned 11 pi over 6 radians and then walked 1, 2, 3, and I'd get to the same point. Now, if I can just imagine, I can spin around as many times as I want to here. And that's going to give me my next idea that I have multiple ways to refer to these points that are polar coordinates right here by just changing the angle mostly is what we're going to do. So any polar coordinate that I have, if I want another name for the same polar coordinate, I can go ahead and leave r alone and add 2 pi to the angle, and I'll go a full rotation around and I'll be at the same place again. Can also subtract 2 pi from the angle like that, and that'll work as well. Another thing that's kind of strange to think about, but this brings up the concept of r is allowed to be negative, is if I'm facing away from where I actually want to travel, I can, quote, walk backwards. So if I want to get out here, if I add 180 degrees or pi radians to that orientation there, then I will be looking this way, and then I can walk backwards my 2 steps and get to the same place. So I can have a negative r comma theta plus pi. Now what I've set up here works for any even multiple of pi. So r theta is going to be equal to r comma theta plus 2n pi, where n is an integer, so 2n is an even multiple there of pi. Or this idea here extends to all odd multiples of pi. And so I can take r theta and change it into negative r, and then theta plus an odd multiple of pi, and that works for all integers n here. That capital Z that's bold there is the set of all integer values. All right, once again, look at this triangle x, y, and r and theta. So this is x, this is y, this is r, this is theta, and we've got this point xy that's out here, and we have this point r theta that's out here, and they refer to the same point in space. So here's the 4 conversions that we were talking about before with the, because this is a right angle here, the Pythagorean theorem comes into play that x squared plus y squared equals r squared. And you know that this Pythagorean theorem is where Pythagorean identities from trigonometry came from by doing these replacements here. The x was equal to r cosine of theta, and y is equal to r sine of theta. Those are important ones there. So, and then we have the other one, tan theta is equal to y over x. This is the slope of the line OP. I call this point out here P. So theorem 1010, coordinate conversion between rectangular and polar. The polar coordinates r theta of a point are related to the rectangular coordinates xy of the point as follows. Polar to rectangular conversions, x is equal to r cosine theta, y is equal to r sine theta. Rectangular to polar conversions, tan theta is y over x, and r squared is equal to x squared plus y squared. So let's go ahead and let's convert the polar coordinates, r theta, and of 2 pi to rectangular coordinates. Let's start there. Let's call this A, and let's call this B. So for A, we have, and I'm going to put P for polar, r theta is polar coordinate 2 pi, and we want to turn that into a rectangular coordinate x, y, like this. So polar coordinate to pi is going to be that x is equal to r cosine of theta, y is equal to r sine of theta, is equal to cosine of pi is a -1, sine of pi is 0, so this is -2, 0 for my rectangular coordinate system. Or for rectangular. All right, now let's look at the polar coordinate system r theta that we want to have as r being square root of 3, theta being pi over 6. I change that to a rectangular system, xy. So x equals square root of 3 cosine of pi over 6. Y is equal to square root of 3 times sine of pi over 6. So x equals square root of 3 times 1 times square root of 3 over 2 is going to be 3/2 for x. And then y is going to be square root of 3 over 1 times 1/2. It's square root of 3 over 2. So my rectangular system coordinate is going to be 3/2 square root of 3 over 2. Now let's convert our rectangular coordinates from this graph here to polar coordinates. I'm going to start with the fact that x squared plus y squared is equal to r squared, which means that r is equal to the square root of x squared plus y squared. So r is equal to the square root of a -1 squared plus 1 squared. R is equal to the square root of 1 plus 1 is the square root of 2. Now, I know that I'm in quadrant 2, which means that my angle, if I'm going to be measuring it counterclockwise, is going to be somewhere between pi over 2 and pi. If I have tan theta is equal to y over x is equal to 1 over -1 is a -1. Then theta is equal to arctangent of -1 plus maybe some n pi, because tangent repeats itself every pi radians. So theta is going to be equal to a -pi over 4 plus pi over 1. And we want to be in quadrant 2 going counterclockwise, so that's going to be 3 pi over 4. So our polar coordinate system is going to be r is the square root of 2, theta is 3 pi over 4. Can you come up with another one? Sure. We can go 2 pi radians around either direction. But I'm going to go the other one and come up with a polar coordinate that's negative √2, and then add or subtract pi to this. So I'm going that way. That's going to be my -pi over 4 there. I'm still on this line. I'm facing this direction. I want to get to that point. So if I'm at this point, instead of walking this way, I'm going to take steps backwards to get there. So let's go ahead and let's talk about slopes and tangent lines in polar equations. So we can use theorem 10.7 here as well. If x is equal to r cosine theta, and we call that r f of theta, then we have f of theta cosine theta, and we can use our product rule here to find what dx d theta will be. And we can say y is equal to r sine theta, which is f of theta sine theta. So this one is going to be d theta of f of theta sine theta. This is going to be d theta of f of theta cosine of theta. By the product rule, so we have f prime of theta sine theta plus f of theta cosine of theta top, and here I have f prime of theta cosine of theta, and then the derivative of cosine is negative, so this can be a negative f of theta sine of theta, like that. Then I take my dy divided by my dx here to be able to get my definition for dy dx, just like we did with parametric equations before. So if f is differentiable, is a differentiable function of theta, then the slope of the tangent line to the graph at r equals f of theta at the point r theta is dy dx is equal to dy d theta divided by dx d theta. There's the chain rule again, and we just figured out dy d theta is f of theta cosine theta plus f prime theta sine theta, and dx d theta is negative f of theta sine theta plus f prime of theta cosine theta. And we need to make sure that dx d theta is not equal to 0 at r theta, or we have a problem because we're not allowed to divide by 0. Now, two observations here is that if dy d theta is 0, I have 0 divided by, and dx d theta is not 0, then I have 0 over a non-zero number is going to give me 0 for my dy dx, and I have a horizontal tangent line. If dx d theta is 0 and dy dx is not 0, then I have a non-zero number over 0 is going to give me a undefined slope, and that's going to be a vertical tangent line. Again, as long as dy d theta is not also equal to 0 there, we're in good shape. If dy d theta and dx d theta are both 0, we can't draw any conclusions about the slope, but we should know that the curve is not smooth. Curve is not smooth at that point, because this is really the formal definition of a smooth curve. Is that if we defined it parametrically, and I forgot to do this last time, I think that a smooth curve has to be able to be broken down into x of t, y of t, with dx dt and dy dt both not equal to 0 at the same time for it to be smooth. Either one of them can be 0, so I can have a smooth curve like the cube root of x that has a vertical tangent with dx dt is 0, but dy dt is not 0, and it will still be a smooth curve. It's not coming to a cusp. But if I have something, so this is like y equals the cube root of x is fine, but if I have y equals x to the 2/3, this is bad. This is not smooth because it comes to a cusp. And dx dt and dy dt would both be 0 there. All right. back into the world of polar coordinates, find the horizontal and vertical tangent lines for r equals sine theta if theta is between 0 and pi inclusive. So we have x we have dy d theta is equal to f of theta cosine of theta plus f prime of theta sine theta. Dx d theta is going to be a negative f of theta sine theta plus f prime of theta cosine of theta. So let's look here and see r, which is equal to f of theta, is equal to sine theta, which means r prime or f prime of theta is equal to cosine theta. So I have dy d theta is equal to f of theta is sine theta. Then times cosine theta plus f prime of theta is cosine theta times sine theta. It's 2 sine theta cosine theta dx d theta is going to be equal to negative f of theta negative sine theta times sine theta, so that's negative sine squared theta plus f prime is cosine. Cosine times cosine is cosine squared. This is cosine squared minus sine squared is cosine 2 theta, and this is sine 2 theta right here. So dy dx, if I'm interested in that, here is going to be a tan 2 theta in just a second. It's really not going to be helpful to me, though. I want to take this sine 2 theta, where dy d theta is 0. This is going to be horizontal tangents. Dy d theta, so sine 2 theta is equal to 0. And if 0 less than or equal to theta is less than or equal to pi, then 0 is less than or equal to theta is less than or equal to 2 pi if I double everything. So where is sine going to be 0 between 0 and 2 pi? So theta, 2 theta is going to be equal to, from 0 to 2 pi is 0 and pi, and also 2 pi, because all of those were included here according to our instructions. So theta is equal to 0, pi over 2, and pi for our horizontal tangent lines. For our vertical tangent lines, we have cosine of 2 theta is equal to 0. And then where is cosine going to be 0 in the interval of 0 to 2 pi? 2 theta is going to be equal to pi over 2 and 3 pi over 2, which makes this theta is equal to pi over 4 and 3 pi over 4 for my answers that will be between 0 and pi. I don't have anywhere where dx d theta and dy d theta were both 0. If I did, I would ignore those. So just did this one. Vertical tangent lines occur when theta equals pi over 4 or 3 pi over 4. Horizontal tangent lines happen when theta is equal to 0, pi over 4, pi over 2, or pi. I just did all the work up there for that. All right, special polar graphs. I'll just mention this in the book and probably leave it at that. There is special graphing software, Maple, Mathematica, some other things that you can use to get some pictures. You can use your calculator to graph in polar mode. Actually, let me show you that. So here and share the calculator as well. So we've talked about how to graph in parametric mode, but now I want to also graph in polar mode. So mode, and you probably want to be in radians when you do this, and make sure that you're in polar mode. When you hit y equals now, you're going to be in an r equals f of theta situation. So let's just try and graph this function right here that was given, cosine of 2 theta over 3, so now the variable switches to theta over 3 like that. I want my thetas to go between 0 and 6 pi. And probably increments of, oh, I don't know. That looks good. I think that's pi over 12. And x is probably going to go from, let's just take a look at this graph. Okay, so that's too much. Let's see, zoom 0 here. There we go. And yeah, so it changed my x and y's for me, kept my thetas the same. And this is what that graph would look like. And you can actually trace it out here. We start at theta is 0 is over here. So just because you have a point at the pole and doesn't mean that you are always starting at the pole, and then advance in theta around, and you're tracing that piece, and you go through the pole, and you have that piece, and they're just going to overlap themselves a whole lot. And we have all kinds of interesting shapes like this that we can get from the graphing of polar equations. So look those special ones up in your calculator. You've got some circles, you've got some ellipses, you've got some things that look like flowers here with certain amounts of petals. Those will be important. And you've got some other things that look like figure eights or an infinity sign kind of laying at an angle. Some people say it looks like a peanut to them. I think those are called lemniscates. And you've got things that are cardioids that look like heart shapes. You've got some things that have dimples in them. And you'll study those things more in depth in other classes, but we're actually going to come back and talk about those things next time. So you might want to have that page in your book handy so you can look at some of the graphs, and we're going to maybe talk about the area that is in one of these polar regions, and we may talk about arc length of a polar region. So that's what we're going to come back and talk about next time, is how we take these graphs and we can identify where the graph crosses itself to help get some of the boundaries. Then we can find arc length and we can find area of those polar regions. That'll be what we come back to next time. So see you for the next video.